Welcome to the next video in the Combinatorics series. We're discussing Chapter 1, Enumerative Combinatorics, and in this video we'll solve exercises 13 and 14. In exercise 13, we want to count the compositions of an integer k in which every part is even. Of course, if every part is even, then k must be even, since the sum of even numbers is even. Therefore, if k is odd, the answer, trivially, is that there are 0 such compositions. But what to do if k is even? The way that I like to think about this problem is to enforce the evenness of the parts by writing k as 1 plus 1 plus 1, and so on. K times. If I then group every pair of 1 plus 1s and collapse them into a single one, then we want these collapsed ones to sum to k over 2, and therefore it is enough to count all of the compositions of k over 2. Now for a fixed number of parts, we know the formula for counting the number of compositions. However, this problem doesn't specify how many parts there must be, and so we can sum over all possible numbers of parts. That is the sum from one part to k divided by 2 parts.
We move on to problem 14, in which we will consider families of subsets. For part A, we want to count the subsets of bracket n that contain at least one odd number. On the screen, I've demonstrated what this looks like when n equals 4. In particular, I've first listed all of the subsets which contain the number 1. After that, I've listed all of the subsets which contain 3 but not 1. Doing so ensures that we do not double count subsets which occurred earlier. Clearly, in general, we would continue the pattern by finding all subsets containing 5 but neither 3 nor 1, then all containing 7 but no earlier odd number, and so on. This procedure for listing the subsets gives away the solution, or at least, a first solution. However, I'm actually not going to pursue this solution. Rather, this was just for warm-up. Instead, we will actually find an easier solution if we count the complement. That is to say, we will count all subsets which contain no odd numbers, and that is to say, we count all subsets of only even numbers. For any n, the number of even numbers less than n is given by the formula n over 2 rounded up. For a set of n over 2 rounded up elements, the number of subsets is given by 2 to that power. Therefore, the number of subsets with at least one odd number is 2 to the n minus 2 to the ceiling of n over 2.
Moving on to part B. We need to count the k-sets in bracket n having no 2 consecutive integers. The solution I came up with for this is a bit on the tricky side, so let me try to motivate it a bit. Suppose that you choose any subset, and let's imagine one of the worst subsets that we could choose. The set of 0, 1, 2, so on until k minus 1. This has only adjacent integers. What we will do is to, in fact, interpret this set as code, so to speak, for another set that we actually do want. We will understand that the smallest element is to be left alone, but the next smallest element is understood to be shifted over by 1. Likewise, we take the next element, which is 2, and shift this by 2. That is to say, it becomes 4. If we continue like this, we will construct the set of 0, 2, 4, and so on. This set will never contain adjacent numbers. Of course, this runs into difficulty. To illustrate, consider the case where n equals 10. If we choose the 3 set of 7, 8, 9, then we will construct the corresponding 3 set of 7, 9, 11. But 11 is an element beyond the parameters of the problem. Therefore, we need to restrict the set we're choosing from. That is to say, we want to make choices from bracket x for some integer x less than n, but what is x? Whatever we pick for x, we know that we will form some subsets which contain x minus 1. For these subsets, x minus 1 will get shifted up by k minus 1 and become x plus k minus 2. This number should now be the largest element that we could choose in bracket n, which is of course n minus 1. What I've then found is that x plus k minus 2 equals n minus 1, which tells us that x equals n minus k plus 1. We are now ready to solve the problem. We will choose k-sets from bracket n minus k plus 1. Each one will be code for a k-set in bracket n, which has no 2 consecutive integers. Therefore, the solution is n minus k plus 1. Choose k. To be fully rigorous, we would need to prove that the map is both surjective and injective. However, the proof of either should be easy, and so I won't include the details here.
Moving on to part C, we need to consider the lists of subsets a sub 0, a sub 1, a sub 2, and so on, to a sub n, which are subsets of bracket n. We want to count those lists which form a chain of proper inclusions. That is to say, every subset is a proper subset of the next one. A crucial component of this problem is that the length of the list of subsets is n plus 1. Therefore, we must start with a sub 0 equal to the empty set and a sub n equal to bracket n. This provides just enough elements so that, for each subset, we may add one element in order to obtain the next subset in the chain. From this perspective, the answer becomes clearer. From the empty set, we choose an element which we will add in order to construct a sub 1. We may choose this element in n ways. Next, we choose an element to add to a sub 1 to reach a sub 2, and we may choose it in n minus 1 ways. Proceeding likewise, we see that n factorial is the number of ways to fill out the chain. For the second part of the problem, we need to consider improper subsets in the chain. Therefore, the length of the chain no longer constrains what the first and last sets may be or how many elements are added at each step. Therefore, the solution to this part is not very much like the solution to the previous part. However, when viewed the right way, it is not a hard problem. Of course, every element must have a unique set at which it appears, or it may appear in none of them. Therefore, we may choose, for each element in bracket n, to put it in any of n plus 1 subsets, or none of them. That is n plus 2 choices for each of n elements. There are therefore n plus 2 to the n ways to do this.